wanted to mention, first of all, can you see my screen okay?
And I can, yes.
Audio's good. I did recognize before I transitioned here, I noticed a few folks in the audience. I'm familiar names, so it's good to see. I think probably the best approach for us is to have me go through the presentation. I'll make sure I leave adequate time at the end so we can, any Q&A and just general discussion we can have at that point. The presentation shouldn't take more than about 20 minutes. And with respect to that, let me start by saying this is a very active area of work in the wastewater industry currently, and it has been now for quite a few years. So I by no means am not an authority on the topic, but what I wanted to do instead is spend a little bit of time just walking through our involvement, King County's involvement in looking at aerobic granular sludge to address a potential future use of the technology within our wastewater treatment plants. I'll start out with some fundamentals, a little bit just gauging by at least the folks I know on the call. There is, folks are knowledgeable about wastewater treatment, but I want to take a minute just to kind of set the stage, and then I'm going to walk through. I call it a storyline, kind of walk through our involvement from starting on a piece of paper through the pilot testing evaluation of a aerobic granular sludge process at our West Point treatment plant. And again, it's important to highlight that throughout the industry, there's a lot of work going on commercializing different versions of this particular process to conduct wastewater treatment, secondary process to conduct wastewater treatment. So with that said, let's go ahead and move hopefully into the presentation. Let's see, frozen up here. There we go. So just real quickly, taking a couple of minutes just to kind of walk through wastewater treatment. I've shown a couple of photographs here, one on the right of our West Point treatment plant and on the left of our South treatment plant down in Renton. Very large treatment plants. I think most of the folks on the call are to some degree aware of the role of wastewater treatment. What I want to do is I want to highlight a couple of aspects of it, and that's going to allow us then to navigate and move through some of the details associated with aerobic granular sludge. So I like to think of a wastewater treatment plant as basically two very large biological processes. And today we're going to be talking to some degree, in some level of detail, about one of those. So you have a liquid stream process, which we typically call a secondary process, where we've got activated sludge or mixed liquor doing a job for us. In addition to that, we also have solids processing, which to a large degree is performed by another biological process via anaerobic digestion in your kind of typical treatment plant. And of course, there are other options for conducting this type of treatment, but right now I just, in a general sense, want to just stage it as anaerobic treatment for solids processing, and then aerobic treatment using a secondary process for liquid stream. So again, fairly large footprints, our treatment plants, constrained footprints with respect to West Point, and that plays a role in this discussion that I'm going to, as I walk through this, is the fact that our current treatment plants, which do traditional conventional wastewater liquid stream treatment, and what I mean by that, removing suspended solids and removing BOD or organics, that is their role. That is the way the permits are currently written to do that. So moving into the world of advanced treatment or additional treatment, obviously there's some ramifications of that in terms of what we would need to do to our treatment processes, and that's again, that's setting the stage for where we potentially see the role of aerobic granular sludge helping us in the future. Again, now kind of focusing in particular on the secondary process. So again, as I mentioned, the liquid stream treatment is termed traditionally, if you picked up a wastewater textbook, it's termed secondary biologic. It's a secondary biological process. And really what this is it's a basically equipment and systems and tanks which are responsible or allow us to control the growth of a biomass. So a biomass, or what we typically call mixed liquor, is basically bacteria, but very diverse populations of bacteria and higher order organisms that are very good, if maintained under a set of conditions, are very good at removing organics and solids from wastewater that enters into the treatment plant. So for our purposes today, I basically want to highlight and just make the point that really it is tanks and mixers and pumps and of those various components and pieces of equipment that make up that infrastructure. Fairly well established, been around for many, many years, the designs and operation of treatment plants, well established criteria and guidance on how to operate them. One other little point I want to make is, because I'll reference this a little bit later, is just for those who may not be aware, is just the terms anaerobic, anoxic, and aerobic. And I'll touch on secondary clarifier as well. So basically the graphic here shows different tanks, and those tanks are maintained under specific conditions. Anaerobic means in the absence of oxygen or nitrate, which is another surrogate for oxygen, or can be utilized the same way that oxygen can. Anoxic is the absence of oxygen by and large, but the presence of nitrate. And then aerobic is the presence of oxygen, the control of dissolved oxygen to maintain that biomass. That material is operated and then transferred into clarifiers, which are just basically large tanks with a cone bottom, and we allow enough time for the solids, that biomass, to settle out and be recycled back into our process. And that clarified effluent, the liquid minus the biomass, becomes the effluent that is discharged ultimately after disinfection, is discharged to receiving body. So that's just kind of a general idea of secondary treatment. Again, I have to set the stage because of the discussion we're going to have about granular sludge. And again, highlighting the advancements in the development of activated sludge. Again, it originally was identified and I would say discovered in 1914 by a couple different working groups. The idea of using sludge and aerating it and its capability of removing organics and clarifying or cleaning up water that then could be discharged with less impact in the receiving water. So that was obviously some time ago, and as time has gone on, we've taken advantage of that discovery and made use of it. Now it's fair to say is the standard in the wastewater industry for treating wastewater at plants. Moving forward, in the early 70s, work was done in looking at, and the term granular sludge started to appear. In this case, it was anaerobic granular sludge, which again is the development of biomass in a granular form in the absence of oxygen. There were applications that were identified here for a lot of industrial pre-treatment processes. So the point being is this was the point or the time at which the idea of granular sludge started to see applications in the industry. Fast forwarding even further, in the 80s, in the existing treatment plants that we see that were based on flocculant activated sludge, there was developments made in what are called selectors or configurations that were specifically designed to benefit or to help improve the settling of that biomass, of that activated sludge in the clarifiers. So our South treatment plant, for example, down in Renton, has a selector, an anaerobic selector, which was incorporated into that secondary process and has done a very nice job of improving the settleability of solids in their process. Moving forward into the early 90s, folks in the laboratory started to evaluate and look at now the idea of aerobic granular sludge. So again, the development of sludge under aerated conditions. And then fast forward to 2011, the first full-scale application of an aerobic granular sludge was installed in Europe. This was a sequencing batch reactor system, which is a little bit different configuration. But at the end of the day, it is known as the first application at full scale of aerobic granular sludge. So with that said, if we move to a discussion of the physical differences, or start to dive in a little bit more into what is unique about granules versus flocculant sludge. I think the photograph tells us a lot. On the left there is a photograph of a typical flocculant sludge, and then on the right, granules. And even without perusing through the table, I think folks would tend to grasp the idea that if you put this biomass into a beaker and left it set, the notion would be that the granules more than likely would settle faster just based on size. And that in fact is the case. I won't go into the details of all the different parameters that are highlighted here in the table. But the point being is that at the end of the day, the granule provides a fast settling sludge, which provides advantages with respect to the operation of a secondary clarifier. You can add more of this to the secondary clarifier. That what we would call the solids loading to a secondary clarifier could be increased if you have the presence of granular sludge. And in addition to that, just being able to take advantage of fewer disturbances or changes in that sludge are really advantages that have exposed themselves over traditional flocculating sludge. Another aspect of it, which folks have obviously spent a lot of time now looking at, is the development of a granule actually allows you to some degree to establish different zones within that. It's kind of traditional fundamental biofilm configuration in terms of you can actually establish within a granule different zones. So as I spoke to earlier about these large tanks that have different zones that we construct and we design and we construct and we operate, the granule itself can be basically grown up and controlled in such a manner that they mimic to some degree these different tanks in a physical treatment plant. So you'll have zones within the granule that will be aerobic, will have dissolved oxygen, and then as you penetrate further in, depending on where you're at, you will find anoxic zones, and then ultimately as well anaerobic zones. So again, it provides an opportunity you'll hear me use the word opportunity a lot because I still think there's a lot of development work left that needs to be done to basically mature this technology. But at least on the surface, it appears there's a real opportunity to take advantage of the granular structure, not only from its settleability perspective, but also the ability to grow and maintain diverse populations within the cross-sectional area of a granule. So a little bit of background on the granules, kind of giving folks a sense. Now, what I want to move into now is I want to focus more on how King County perceives and did perceive several years ago an opportunity to potentially utilize this technology. So the graphic I'm showing here was originally sketched up, and I would argue probably on the back of an envelope to begin with, but was sketched up by Professor Dave Stencil at the University of Washington and Bryce Vigdor and others along with some of our county staff in an early idea on how to address what we knew most likely would be potentially a future permit change that we may see in our treatment plan, associated with our treatment plants. In particular, what I'm referring to is the notion of needing to take our existing wastewater treatment plants, which, as I mentioned earlier, are BOD and TSS only removal plants, is to convert them to remove nitrogen. And obviously there's fundamental ways, textbook ways of converting treatment plants. Obviously those conversions can come at large capital expense as well as operating expenses. And there are the given complexities as well with adopting and converting those treatment plants, not only in operation, but even implementation and during construction. So the idea, I say we in a general sense, I think there was a group that thought, well, you know, having observed the development of aerobic granular sludge, there was potentially an opportunity to use the idea of aerobic granular sludge to basically retrofit an existing treatment plant to get some portion or some nitrogen removal with roughly the same infrastructure that you currently had in your treatment plant. And the way this was to be accomplished, or the idea that was on the back of the envelope, was by bioaugmentation. So bioaugmentation is simply taking an existing process, continuing to operate that process under the same conditions, but then bringing in, quote unquote, augmenting the system with another material and another substrate or another aspect. And in our case, this was granules. And the idea in which to accomplish this was, one, you had to figure out a way to grow up granules. And that's what this bottom portion is all about. The idea was to use centrate, which is a flow that's readily available in the treatment plant. It's basically off a dewatering process, so it's digested sludge gets dewatered to generate a biosolids, and the centrate stream that's returned to the treatment plant is rich in ammonia, lots of phosphorus in it, has lots of alkalinity, and so the idea was to take advantage of that, and at the same time take advantage of it with respect to being able to grow up granules. And so the notion was to operate a reactor, which was would be a sequencing batch reactor, feed it centrate, feed it other substrates, and maintain a set of conditions within that reactor such that you would actually generate granules. granules of the nature that I referenced earlier. Those granules would then be actually discharged back into the secondary process at the existing treatment plant. That secondary process would not change their approach to maintaining their flocculent sludge or their mixed liquor, but the addition of the granules potentially could serve as a means to grow up the bacteria required to convert and remove nitrogen. So the idea was you run the side stream reactor, you have a steady stream of granules you're generating that gets put back into your process. And again, as I highlighted before, that secondary process of the granules, there's a good chance you potentially then would have improved settling conditions in your clarifier. So your effluent would not be impacted from with respect to traditional effluent quality. Plus you would be getting the nitrogen removed. So that's all fine and dandy, but then the way that you would need to manage that system is that those solids that you settled out and returned to the process, eventually for process control purposes, you had to waste some of that activated sludge. But what you don't want to do is you don't want to waste the granules out. You want to keep them because of the role that they play that is different than the traditional role of the flocculating sludge. So there's a mechanism you would have to put in to separate the granules out from the floc. You would waste the floc away. The granules that were captured, again, would also be returned. So now you have two independent systems that you manage. You manage a flocculant system and you manage a granular system. Now this looked really fantastic on paper. And so there was a lot of real interest and enthusiasm at really seeing if this had potential. And so we all looked at each other and we said, and so Professor Stencil and I started talking about, well, how can we take a look at this at a deeper level? So we took advantage of another unique aspect that we have in King County. And that unique aspect is that we have maintained a graduate fellowship research program with the University of Washington Civil and Environmental Engineering Department for many years, 25 plus years. And so it only made sense. And the role of that research program was really to address applied research questions or problems or issues that we had in our treatment plants. And so this idea of bioaugmentation with granules was a no-brainer that it fit nicely into this to this program. So we chose to pursue the development of the configuration through the graduate fellowship program. And I will note as well, over the course of this, Professor Stencil was able to, along with Professor Winkler at the University of Washington and Professor Stahl, were able to capture funding through the Water Research Foundation as well as through the National Science Foundation to support this development work. What I want to do now is I'm going to walk through the work as it played out through the graduate research program. And another reason I focus on this is I think it's a really good template or a really good model, or it's a really nice way to show how typically innovation works or could work in the wastewater industry, in particular. How one goes about developing a technology and the pitfalls and the hiccups along the way. So let's start with Bryce Vigdor. Bryce who currently works for HDR. He came in to do his PhD work at the University of Washington, working under Professor Stencil. And Bryce he was there from 2014 to 2017. He probably wouldn't like me actually throwing those dates out, but it's a traditional PhD program. And what he did is he was able to successfully show in the laboratory at the University of Washington, he showed two very critical aspects of the development of this technology. He showed at the bench scale that you could grow granules up on centrate. I mean, and not only that, he also showed or identified what more than likely were the better granules to grow. And what I mean by that is there were options where you could just grow up, as termed here, nitrifying granules, or there's also the idea of growing up a granule with a existing PAO population, or that is enhanced by making sure that you maintain a PAO population. And a PAO is basically a phosphorus accumulating organism. It's typically used in biological phosphorus removal systems. It's well studied, and over the course of his work, he found that the granules that he produced while he was making sure that he maintained a PAO population had advantages over a granule that was generated that just operated with nitrogen, with ammonia removal. So long story short, he was able to show this convincingly at the lab. I won't go through this table. I have it here just to kind of for folks to look at on their own, or if you have questions, we can walk through it. But basically identified the operating conditions which made sense based on his work at the bench on how to grow those granules up on centrate. And it's fair to say, I need to highlight the fact that he was using centrate from West Point. He was not using a surrogate feed source. So that actually even, typically in our minds, if we're using real wastewater process flows, that even added to that it made sense to his results were defendable. The second part of his body of work, which again is I think pretty amazing, even though it's small scale, is he actually also confirmed the potential of bioaugmentation. And the way he did that was he had a small sequencing batch reactor that he ran in the lab. He fed it and maintained a flocculent sludge population that did not nitrify. So there was no nitrogen removal. What he did then, and what this graphic is intended to display, is he took the granules that he was growing via his side stream process, and he added those granules into this small SBR reactor. And I think proves pretty dramatically, as you can see here, the horizontal axis showing days from the initial bioaugmentation. So this is when he added the granules. This is influent ammonia loading was consistent throughout the test, and this is the effluent ammonia that basically the effluent he got out of the reactor. And you can see very clearly that just after bioaugmenting with the granules, you get near 100% ammonia removal, and you also are getting conversion as well of the nitrate and nitrate from the process. He maintained that condition for 40 days. Then he actually took the biomass, sieved out the granules, returned the flocculent sludge to this small reactor, started operating again, and lo and behold, he was able to show that the ability to nitrify or ability for nitrogen removal was removed. And then obviously conclude that the capability was centered around the granules that were bioaugmented into the process. So this body of work, along with the centrate, the granular reactor system, this work basically made up his PhD dissertation. And for those that are interested, want to read further on it, It is available. Go take a look at it. It's great. He did a fantastic body of work. And for our purposes, for King County's purposes, he allowed us to check off boxes and move into the next phase of our evaluation of this technology. And that next phase involved Max Armenta, who is a master's student under Professor Stencil. At this time, we took Bryce's work, and Professor Stencil designed a side stream granular reactor, a pilot, which is shown here in the photograph. We being King County, fabricated all of the reactor itself using our maintenance staff in our treatment plant, as well as our instrumentation and control folks, and we basically built this side stream reactor system at the West Point treatment plant. The intent there was to scale up, obviously, the work that Bryce had done, and actually look closer at the operating conditions and control strategies needed to grow and sustain granules via this side stream reactor system. So happy to say this side stream reactor ran for 2 years. We were feeding it centrate from the treatment plant. Max did a tremendous job monitoring, evaluating, and enhancing the controls, as well as the ability to maintain and troubleshoot the reactor. It's fair to say that this was successful in clearly showing that a reactor system like this could be operated in a treatment plant. Another thing to note, and this is just kind of, I think it's really interesting to observe. If you track the photographs here are basically the development of the granules, starting back in February of 2018, and just progressing through and seeing the different characteristics, just visually speaking, of the granules and how they were maintained. Another side note real quickly, also to point out, is we had some real questions about how we would start this granular reactor, and Professor Stencil had an idea, and so we pursued it. We collected some samples from our South treatment plant, which we knew had an active PAO population because of the selector that I had mentioned earlier, had been operating in that plant. Collected samples and did some work at the university and confirmed that there actually were small granules already in the mixed liquor, in the activated sludge at our South treatment plant. So I don't include the pictures here, but I find it a bit humorous. So for a day back in February, Max and a couple of other graduate students from the University of Washington, I met them down at South Plant, and they spent a good portion of a day sieving mixed liquor in the plant to basically capture a seed source for starting this reactor up. And it's fair to say that it was successful in doing that, and I think saved us quite a bit of time, and also, again, would highlight a mechanism or a way to start up a reactor like this at full scale. And it highlights the importance of PAOs in the development of granules. So Max's work finished in 2019. He was at the U and worked on the pilot from 2017, 2018, 2019. After we showed this, the next step was, well, what we need to do is we need to build a mainstream secondary, a secondary process in the pilot, at the pilot scale, in which we could use these granules and confirm that bioaugmentation. We were able to actually bioaugment an existing flocculant-only secondary process and get nitrogen removal. So I'm not going to go through the details here. It's fair to say, there's the system. I guess I'll highlight a couple of things. So the choice was made to include some different tanks in this secondary process, which could potentially help us to maintain the granules once they were bioaugmented in here. Another key element in here was a challenge, to say the least, was to figure out a way to separate the granules from the flocculating sludge. And I'm highlighting that here because that is one of the conclusions or observations that we made when we ran the pilot that proved to be quite difficult, at least in the configuration that we had. So John Carter came on board as a master's student in 2019, worked in 2019 and 2020 to support the operation of this secondary process in a reactor system at our West Point test facility. So I already shown a picture of the side stream reactor. Here's the infrastructure that was installed to mimic a secondary process. We brought primary effluent from the treatment plant into the pilot area. It was the feed to the secondary process. We installed instrumentation to monitor the system. We tried as best we could to mimic a secondary clarifier at a very small scale. This proved to be a challenge in and itself. But at the end of the day, we started up and operated a secondary process and bioaugmented with granules that were grown up on centrate. Unfortunately, we only were able to operate roughly 30 days before the onset of the COVID-19 pandemic. But we did have enough operating time to draw some conclusions or have some observations. And I've highlighted these, bulleted these for our purposes, or for the purposes of just sharing. All of this information is also being captured or will be captured in a final report from the Water Research Foundation and would be available for those interested. But a couple, just to highlight, we were able to confirm granular growth in the mainstream reactor based on the configuration. We did get nitrogen removal, not as much as we would have liked, but we did identify nitrogen removal via bioaugmentation. And as I highlighted previously, the idea of incorporating a separator for separating the granular sludge from the flocculant sludge, we had a lot of difficulty in doing that. And so we had very poor separator efficiency, which played a role in the lower than anticipated nitrogen removal efficiency we saw. In addition to that, it was noted granules were breaking down. There was degradation. We hypothesized that part of that at least was due to the scale, more than likely. It's difficult to install pumping systems at this scale that potentially don't exacerbate and elevate the risk of breaking granules down. But at the end of the day, there were some modifications identified. We are not currently pursuing those modifications. We are still very closely monitoring and watching the development of granular sludge. We're working on right now on the design of a pilot to look at another media-based technology that would mimic granules. In any case, I just wanted to finish up by just noting, again, highlighting, I guess, that there's a tremendous amount of work going on in the industry right now with respect to aerobic granular sludge. There is a process, at least one process that is fully commercialized and is being installed in treatment plants, and that's the Narita process, which is a sequencing batch reactor system. That's proven, many installations, and again, a well-established, well, I would argue a fairly well-established technology. The one that I think is kind of, I guess, quote unquote, I've heard it termed the holy grail, is to identify or develop a technology which is applicable in a continuous process flow system. And what I mean, sequencing batch reactor, obviously you're not feeding 100% of the time, but in a conventional treatment plant, which are continuous flow systems, is to implement or looking at different ways to implement the idea of granular sludge within those treatment plants. I put it here just as a reference. Part of that development is really methods and means to separate granules and enhance the capture of granules in a flocculant sludge system. And so one method for doing that is a hydrocyclone, which is seen. There's a lot of work right now and a lot of trials going on to look at that. In that case, not only would it advance the improvements potentially in secondary clarifier operation, the settleability of sludge, but also could have implications with respect to enhanced nitrogen as well as phosphorus removal. So that's the gist of my presentation. Again, I just want to highlight a couple of quick things. All of the information I ran through it should be readily available either through Final Report and Water Reuse Foundation or through University of Washington in terms of a thesis or a dissertation. In addition to that, again, I want to thank everyone who has been involved in this, from not only from King County, but the University of Washington, and the longstanding graduate research program we've had with them has been fantastic and has really helped us to learn a lot about granular sludge, as well. I think helped the industry in terms of getting a better grasp on the potential opportunities out there. So with that, I will open it up to Q&A. I know there's at least one person on the call who is really well versed on granular sludge, so I'm interested to hear any. Doesn't have to be Q&A, could just be general discussion. In any case, I'll leave it at that.
Great, thanks, Bob. Yeah, like Bob said, feel free to ask questions. It can either be in the chat if you want to write it all out, or if you want to turn on your mic or turn on your video and ask questions that way, we can do that. But it looks like we have a question. I don't know if you wanted to read it or you want me to read it there, Bob.
Let me pull it up here.
Sure.
So is this one from Steve Burgess? No.
It is.
I didn't see another question. Is there one there?
It's just that one text that says, "Thank you for your presentation."
Yeah, no, and part of the point, recently, Dave Stencil passed away, so it's been a real struggle for us, folks closely connected with him and working in our fellowship program. It's been rough. I mean, he had great contributions to the industry, and he will be sorely missed. Any other questions? Discussion? Come on. I'll start picking names because I see the names here. No.
What's up, Bob? Robert from Infrastructure Week. I've been tuning in from the job site down here in the Bay Area, so just saying what up. Good presentation.
Good, thanks. Appreciate it. So I guess one thing is people kind of ponder a potential question. One thing, again, it's fair to highlight that there is a tremendous amount of work going on, not just regionally here in the Northwest, but across the U.S. So Whether this plays out for us in the long run, we'll see. I think there are some real challenges in the development of granular sludge. I think maintaining integrity is one. Really, truly seeing how much of an advantage that it can play in the long run in the year-to-year daily operation of a treatment plant, I think will be interesting to see how that plays out. I think people have scratched the surface on the potential. But as I showed in my timeline, it does take quite a bit of time to develop not only the idea with respect to treatment, but also the best practices for how to maintain and control. And an example of that would be the side stream reactor that we ran for 2 years. We identified intermittently inhibitory activity. So we lost some of the nitrogen removal capacity in the side stream reactor when we were developing granules. And we had all kinds of ideas on what was causing that, but I'm not sure we necessarily were able to thoroughly vet what the cause was. And so, and it's clearly documented in Max's thesis. And I'm sure in the Water Research Foundation project, but it's something that will need to be addressed. And it's tough if you're a consultant, for example, and a utility asks you to design a system for them that incorporates granular sludge, is what design factors or what kinetic parameters do you use to even go through that design, and feeling comfortable with minimizing the risk that in incorporating that into that design and ultimately the performance of the treatment plant. So.
Well, we still have a few more minutes if anybody wants to ask a question, comments, concerns, or I think Bob's ready to pick on some people too.
Well, no, I won't pick on them. Well, I guess if I'm not hearing any, I would just again comment. I know WEPTEC. I was looking at the upcoming WEPTEC conference. I know there's going to be a lot of discussion on granules there. Animox, by definition, is a granule. That term is used, and that's another area of research. And I know in PNCWA regionally, there'll be some discussion on granules, I'm sure. And then there's a lot of people looking at it. And I think any way that we can network and share lessons learned and advance the development of the technology, the better and the quicker potentially we could get to a point where we've got another alternative. Because if you work in a treatment plant, you always love to have alternatives that might be a little bit more robust and help you to get through the day a little easier. Even though flocking with sludge has been around forever, it still gives us lots of headaches. All right, quiet group.
Yeah, last call.
It's the problem with lunch and learn. People eat, and then you want to take a nap. I have not eaten yet.
All right. Well, without any questions, thank you again, Bob. Very informative. I appreciate you taking some time out of your day to present to our group. Thank you, everyone, for being here. A quick reminder, our next meeting is on September 16th. It will also be virtual. The topic will be urban stormwater chemistry and its impacts on sediments. So with that, have a good afternoon, everyone, and we'll see you next month. Thank you again, Bob.
Have a good day.
Bye.